Okay, so this is the oscillation questions. Okay, so for question 9, A, first thing, what is the total energy? Now, for total energy, the formulas is pretty fixed. Total energy is the maximum energy, half m omega square x naught square. We can straight away use this. Okay, because V naught equals omega x naught. So this is actually the maximum KE. Now, the mass is given to you, 0.12. Omega is 2 pi over T. So 2 pi over 0.18. X naught is given to you. Okay, 0.30 square. So from here, just press into your GC to calculate. Okay, times 2 pi divided by 0.18 square times zero point 0.3 square. So net I get 6.5797 which is approximately, then we look at them, the raw data or 2SF, we'll just put 2SF, 6.6 joules. Okay, all the raw data. So part 2, where is the mass where K is equals to 0? Definitely is at rest, so it's at the amplitudes. Okay, so this is a giveaway question. Where is the mass when K is equals to the potential energy? Now this is a little bit trickier. Means where is X? So because of that, part 2 we also need to say where is it. So X equals to negative 0.3 or X equals 0.30. So it's at the amplitudes. Okay, let's make it nicer. Okay, so for part 3, half m omega square x square. Now this one is the potential energy is equals to half m omega square x naught square minus x square. Okay, so we can see that the half m omega square repeats. We can actually cancel out, which makes things easier. Okay, this is actually to be more proper, this is the potential energy and this is the kinetic energy. So when they are equal, uh, you'll get, you get 2x square equals to x naught square, or x equals to plus minus square root 2 of x naught. Now x naught is 0.3, so it's equals to negative root 2 times 0.3 or root 2 times 0.30. Okay, so we need root 2 times 0.3, 0.3 times root 2, and we get negative 0.424. Oops. Negative 0.424 or 0.424 joules. So not joules, meters. Okay. Uh wait, I think there should be a careless because it should be within 0.3. So we need to find the careless mistake. Okay. So okay, so it's actually when I bring over, it's actually 1 over root 2. So that's where the careless is. Okay, 1 over root 2, 1 over root 2. So you can see sometimes the careless is pretty obvious and we need to keep checking. Okay. So let's redo this part. Divide by 2. So root 2 divided by 2. So it's actually 0.212. 0.212 or or positive 0.212 meters. Okay, so it's either of this. Yeah. So that is the answer. Now, that's for part A. Part B. A vibrating system which is made to undergo forced vibrations may exhibit resonance. So explain resonance. Okay, let me just shift this diagram. Now, explain resonance, right, is basically just the definition. So this should be pretty simple, pretty straightforward. Okay, let's make this bigger. Okay, so resonance. Let's make this bigger. So we need to explain what is resonance. Resonance is the phenomenon where an oscillatory system responds with maximum amplitude when the driving frequency on the system is equals to its natural frequency. So the key thing is about maximum amplitude and driving frequency equals natural frequency. Okay, so indicate how the amount of damping can influence resonance. So basically, they are asking about the resonance curve. Okay, means you describe the resonance curve itself. So as the damping increases, if you can recall from a resonance curve, as the damping increases, okay, the maximum amplitude decreases, and the resonance occurs at a slightly smaller frequency. So we can actually add that in because that is what we mentioned as the amplitude is lower and it tends towards the left. Okay, so normally when we draw our frequency response graph, okay, the amplitude and the frequency, okay, what we draw is we go up, they go down is for no damping, and then we draw them with a tendency of a broader and broader. Okay, that's supposed to be amplitude here. No, sorry, supposed to be an asymptote here. We draw with a tendency towards the left, you can recall. Okay, so what happens is that the maximum amplitude now occurs at a slightly smaller frequency because of that. It's towards the left. Okay, and it's actually also lower. Okay, because damping causes energy to be lost. Okay, so this is for B, part one. And part two, give an example of a situation where resonance is useful, what is the oscillating system, and what forces it to resonate. Okay, so this is in the notes. School notes should have as well. So we can actually use a situation of a tune mass damper. Okay, and the tune mass damper, which is used for architecture, used for buildings. So in a tune mass damper, so this is where it's a situation. Okay, example. It's an example where resonance is useful. The oscillating system is the tune mass damper, and what forces it to rotate, to resonate, okay, uh, is what happens is that when the building shakes due to external influences, which could be earthquakes or wind, okay, it shakes or vibrates, okay, it 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 provides a driving frequency, a periodic driving force. Okay, to be more proper, it provides a periodic driving force to the tune mass damper. Okay, what forces it to resonate? We need to say more. Okay, the mass damper, the tune mass damper, has a natural frequency that is similar to the buildings. Okay, let's go down to the buildings natural frequency. So when the building vibrates, when the building shakes, its natural frequency, its driving frequency, this is a bit long, so you might want to summarize. The driving frequency is equal to the natural frequency of the tune mass damper, hence resonance occurs. Okay. Now, if the question asks why there is maximum amplitude, then you add in there is maximum transfer of energy. If not, we can just end it at here. Okay, because the question only asks why, what forces it to resonate. That's all.